My name is Liberias and I am going to discuss about KNN nearest model for search queries anatomy detection. First, we need to know about what is search queries anatomy detection. This is the process in which we identify or locating specific body parts or structures within medical images like X-rays or MRI scans. This is important for doctors to diagnose and treat health conditions accurately. Now we need to know what is K nearest neighbor model, KNN model. It is a simple yet powerful machine learning tool used to help with this task. It works by looking at the features of a new dataset points and comparing it to non-data points. It then classifies the new images based on the closest matches it finds. Using the KNN classifier for search anomaly detection means we can automatically and accurately identify different body parts in medical images. This makes the diagnostic process faster and more reliable, helping doctors make better decisions for patient care. For better understanding, let's move to our compiler. Here in the first step, we import some libraries to perform different functions. In this first step, we load dataset. Load dataset, we already load dataset here, queries CSV. By using its path, it's here. We can access this file, and here this some dataset of. We can see that here all the data include in this queries CSV file showing here. Now in this process you can see that we start by loading the dataset containing search queries. Here you can see that CTR column originally a percentage string is converted to a float for numerical analysis. As it is important to convert the str percentage into float, you can see that in this table of str all the values are in percentage. We can convert it into float. Here in the next step, features and target separation, let's run it, and in this code the dataset is split into features X, and you can see that here slicing occur, and all the columns except the first one showing, and in the Y column target Y only the first column is showing. In data splitting and scaling, the next step is encode categorical data here, and the next step is split data into scaling. In this the data set is split into features X and Y, then we convert the target value Y encoded to convert the categorical label into medical data, and then that data is split into training 80% and testing 20% sets. Feature scaling is performed using standard scaler to normalize the features, and the equation is x scaled equal to x minus mu and divided by sigma. This is the basic use standard scalar equation used in this process, in this code. For to fit our model, we can use this statement piece of code, and in this way the best KNN model with the optional K is the retrained on the entire training set and used to make predictions on the training set. In the next step, we are using make predictions, and in this step we evaluate the model using confusion matrix, shows the count of true positive or true negative, false true and false negative predictions, and classification reports, provide CN recalls, and first F1 score for class, and accuracy score, overall accuracy of the model. Here is the most important piece of code, apply KNN classifier. This is the basic code of our model. In this KNN classifier code, we differently use K values. For each value of k, fit the Cannon model value on training data, predict on the testing data, calculate the accuracy score, and accuracy formula we can use the number of correct predictions divided by total number of predictions. We choose the best k based on the highest accuracy score. This is our last piece of code in which we are going to import MATLAB library PLT to represent our observation into a histogram. A histogram will legend the class distribution in the training data, helping us understand the balance of the classes. You can see that here. This is our histogram. You can conclude that this project demonstrates the application of Cannon mode algorithm for detecting anomalies in search queries. By tuning the number of neighbors k and evaluating the model's performance, we can effectively identify queries that may require further investigation.
Hello everyone, today I will be explaining how we used two machine learning models, one class SVM and isolation forest, for searching anomalies within a search query dataset. So just to give you a brief recap on what is anomaly detection is basically identifying outliers from our data or pattern. This means this could either have negative or positive connotations depending on applications. If it is a positive connotation, it could mean new research areas or gives us customer usage forecasts. For our applications, search queries, which is our day-to-day browsing, it does have positive connotations. Now that has been cleared up, let us look at our data set. So our dataset consists of 5 main columns: top queries, clicks, impressions, CTR, and positions. Our 4 main metrics, however, are the clicks, impressions, the click-through rate, CTR, and the position. Now I would like to explain what these metrics mean, as they are the basis for our project. So the clicks are basically the number of times a user clicks on a particular search result. This metric directly indicates user engagement with your website. If there are a high number of clicks, it means that the result was relevant and that met the user's requirements. Next, we have impressions. This basically means how often your website comes up in the search engine's result page. This means, for example, if I search anomaly detection, it means how much DataCamp's website comes up on the search results. And as we can see, it is at the top of the page. That means it has highly relevant content. So as a result, a high number in this metric indicates that the website pops up on the relevant search queries. However, keep note that this does not translate to clicks. Next is a very important metric called click-through rate, or CTR. This is a derived metric. It is the ratio of clicks to impressions. What this means is that once your website was displayed on the results page, how many percentage of the users actually clicked on the website? So what does a high CTR mean, though? A high CTR is a very good metric. It shows that your website is displayed on the relevant search results, but it also entices the users to open your website, meaning they found the needed content and find it highly relevant. Our last metric is position. This refers to the ranking on the search engine result page for a specific query. This metric essentially indicates the prominence of your website. To understand how this metric works, the closer it is to the value of 1, as we can see 1.61, 1.02, it means the higher the position, and the further away it is, the less relevant it is against the search query it was searched up against. Now that we have an understanding of our data set, let us look at the code. So first of all, we have used one class SVM. Let us look at our libraries. We have imported pandas for data manipulation, Plotly Express and Plotly.io for further data visualization as needed. We have in this line, we have imported our queries to CSV file into a data frame, and we have printed from the top of the data set to give us a quick visualization of what our data looks like. Dimensionality is equals to columns means that we will be printing the dimensionality of a data to understand whether it is a low dimension data set or a high dimension data set. As we can see, the dimensionality of a data set is, which means that it is a high dimensional data set. Next up, we will be doing some data pre-processing. Data pre-processing is a crucial step in cleaning our data. It is able to address common features. It is able to address common features like different scales and outliers that can affect the behavior of a model. We will be doing further data pre-processing as we use the different models. This data pre-processing step is applied throughout the project. This basically means that it scans the CTR column and removes the percentage from the float. As we can see over here, our model will not be able to read the data with the percentage sign. So this basically removes the percentage signs and checks for any missing values. If there are any missing values, a 0 will be put into that place. Now, next, we have created visualizations for the most common words. As we can see, the most common words use Python, in code learning, and so on, in a decreasing trend. We have created a function called clean and split, and we have passed each of the queries within this. This splits words between lowercase letters and capitalized words, and converts the capitalized words into lowercase. Next, we have shown a visualization for our top queries by clicks, as we can see. The mechanism game is at the top of our graph with 5,223 clicks, followed by the clever programmer at 2,800 clicks. Top queries by impressions is again Python projects with source code. This matches with our previous visualization of having Python at the top, with having Python as the most common word in our most searched results. Next, we will be looking at, as I mentioned before, one of our most important metrics, the click-through rate. So at the top of the click-through rate is the clever programmer, 2 websites from the clever programmer, and at the bottom part of our click-through rates are Python Turtle and Standard Scalar with very low click-through rates to an impression ratio. Now moving on to our algorithm implementation. We have used the pandas library for data manipulation and sklearn library, which is a very popular library to import machine learning algorithms, and the matplotlib library for further data visualizations to showcase our results. Now, first of all, let me explain what is one class support vector machine. It is basically an unsupervised learning algorithm, as it does not need any labeled data for normal points and anomalous data points. So how does this model work? This model learns the behavior and characteristics of the normal data in a data set. After this identification, it attempts to define a boundary around these normal data points, and classifying anything outside of these data points that deviate significantly from the boundary around our normal data points as anomalous data points. In SVM features is equals to queries df, we have chosen our 4 main metrics: clicks, impressions, CTR, and position. Next, we have done feature scaling, which comes under data pre-processing. As I mentioned before, pre-processing is the crucial step in machine learning. As we can see from our dataset, these are varying scales that we use. Some are in The lower bounds, for example, they are in decimals and floating, and while others are in percentage and others have very high value, as impressions has very high values as compared to clicks. It is important that we bring all of these on a standard scale so that they can be usable by our machine learning model, and there is no unnecessary bias, a bias that can affect our model. So how does the standard scaler work? It takes each feature, clicks, impression, city, and position, and subtracts it by the mean of that one feature, and then divides it by the standard deviation of that feature. This ensures all features contribute equally, and no unnecessary bias is introduced, as I mentioned before. Now, moving on to the model, we must take into consideration three parameters in one class full vector machine: mu, kernel, and gamma. Now, what do these parameters mean? Mu. It takes the upper bound of the training portion of our data and allows it to be classified as anomalies. What does a high NU mean? High nu mean? High nu means that the decision boundary is more flexible or is softer, meaning that it can capture more data, more normal data points. However, it can also include outliers. Lower NU makes an inflexible or stricter boundary, which makes it more susceptible to missing anomalies that deviate slightly from the boundary. Okay, so next step is the kernel function. The kernel function transforms the data into a higher dimensional space to capture more complex relationships between the metrics. As the data is nonlinear, we have used a real basis function, or RBF, which is a popular choice for nonlinear data. It allows the model to learn relationships in the higher dimension, which fits well with our dataset. Lastly, the last parameter used is gamma. Gamma was used due to our inclusion of the kernel function. It essentially tells how much each data point has an influence on the decision boundary, which was made in the higher dimensional space. A high gamma increases the influence of more data. This results in a more harder decision boundary that might be prone to overfitting against each data point, thus making it sensitive to outliers. However, a lower gamma creates a smoother boundary, making it less sensitive. Due to the less sensitive nature of the boundary, the model might miss data points that deviate slightly from the boundary, thus meaning that anomalous data points that are not very far from the boundary can be included as a normal data point. Let's move on to the training of our model. So SVM model.fit scale features is basically training the model and draws a decision boundary around our normal data points. Next is predicting our outliers. This predictions is used SVM model to predict basically assigns prediction scores. 1 means that it is a normal data point, whereas -1 indicates that it is an outlier or an anomalous data. And outliers is equals to crazy if predictions is equals to -1. Selects all rows with -1 prediction and creates a new column called outliers, where only the rows with -1 predictions are included. Query CF anomaly is used to SVM model. This is a simple line of code that makes a new column called anomaly in a data frame and includes all the anomalous features in this column. Next, let us look at the results of search query anomaly detection. As we can see, amongst the 1,000 data points, we have collected 8 anomalies from our one-class SVM implementation. This is a histogram to show the frequency of the anomalous data points against the click-through rate. So next, we are utilizing isolation forest to detect anomalies in search queries. Again, we have used the sklearn library to import our isolation forest and silhouette score. The isolation forest is an unsupervised machine learning algorithm which is developed specifically for anomaly detection in 2008 by Fei-Tony Liu and Xihua Xu in 2008. And next, we have also imported silhouette score for further evaluation of the accuracy of our model. So how does isolation forest work? Isolation forest uses binary trees to detect anomalies, which results in a linear time complexity and low memory usage, making it useful to process large datasets with a higher dimensionality, which is highly relevant for our dataset as our dataset has a dimensionality of 5. It is similar to one-class support vector machine, and it does not use labeled dataset, thus making it an unsupervised learning algorithm. The basic idea behind it is that anomalies form a branch in the tree much earlier and easier as compared to normal data points. Let me give you a step-by-step explanation as to how this works. It first chooses a random feature from our available features, which is clicks, impressions, CTA, and position. Suppose that it takes the clicks feature. The branching is done by selecting a random value from the chosen feature range, meaning that it takes from a minimum value to the maximum value, it takes any random value within this range. If the value of the chosen data point is less than the selected threshold from the range, it goes to the left, it makes a left branch. However, if the value is greater, it makes a right branch. This is done recursively for each data point until each data point is completely isolated or the maximum depth of the tree is reached. This is done for each feature, which makes an ensemble of isolation trees, or basically a collection of binary trees or isolation trees. So how are anomalies classified? The normal data points make deeper branches in the tree. So they take multiple splits to isolate and thus make a deeper path to reach the leaf node of that data point. Whereas anomalous data points are easily split and isolated. They make much shorter paths to the leaf node. In our algorithm, 1 indicates a normal data point, whereas -1 indicates an anomalous data point. We have created a data for, now let us look at the coding of isolation first. We have made a data frame where we have stored clicks, impressions, CTA, and position. I've stored them in the features variable. And we have initialized our isolation forest within this variable, which contains 2 important parameters, N estimators and contamination. Let me explain what these parameters mean. N estimator specifies the number of isolation trees to be built in the ensemble, the collection of trees. We have given 100 in our case. That means there will be 100 binary trees or isolation trees that will be made in our ensemble. Next is contamination. This indicates the percentage of expected anomalies in the data. This is set to 0.01, meaning that we are to be expected to have 1% anomalies from our entire data set. Next, we are fitting the model, means that we are training the model. It learns to isolate data points that deviate significantly from the chosen features. Next, we have phrase df anomaly is equals to isoforest or predict, which, which means it is training the data. Next step is filtering out these anomalies. So this uses a trained model to predict anomaly scores. As I mentioned before, 1 is when our normal data points and -1 is -1 are anomalies. It makes a new column called anomalies in this data frame, and all anomaly data points are entered over here. Anomalies is equals to praise df. It basically makes a new data frame called anomalies and includes all the rows where the anomaly score is equals to 1, giving us a separate data frame for us to have a quick glance at all the data points that have been classified as anomalous. Now, we have used a silhouette coefficient to measure the accuracy of our data point. Silhouette score basically measures the distance between each data point. The further the distance of each data point, meaning that it is more accurate. As we can see from our data point, there are multiple anomalous data points that have been classified, and they have very high distances between each other, which makes it an accurate algorithm. However, let us look at the code and what results do we get. We pass our anomaly data frame into the number of anomalies and pass it to the silver coefficients form, which we have imported from our scikit-learn library. So the total number of anomalies we gain with 10, and the silver component coefficient is 0.917, and so on. To understand this result, we need to take into consideration that the closer it is to 1, the more accurate the score. And the closer it is to -1 means that it is less accurate. As we can see, our value is very close to 1. That means our algorithm is highly accurate. This is a scatter plot to indicate our anomalous data points against the normal data points, and this shows the frequency of anomalous data against the click-through rate. We have shared all the results in the following report. We have given abstract to give you a glance of what our research has done. Includes an introduction of why search query anomaly detection is important. Discusses the types of anomalies to be expected. Why search query anomaly detection is important from a business point of view. Thus, anomaly detection methods, which include 3 types: visualization, statistical method, and machine learning models. And in our project, we have used 3 machine learning models: k-nearest neighbors, one class is for vector machine, and isolation forest. Next, we have done feature engineering to clean our dataset. And we have shown all our results in the report. Next, we have explained all 3 of our models, how data pre-processing was done for each model, the model training and evaluation, optimal model selection, and performance metrics for each model, and we have also included the final results for each model, as we can see over here. And this is the final comparison of search query anomaly detection between one-class SME and isolation forest. Through a visual inspection, we can see that isolation forest is the most optimal method. This is also due to the fact that isolation forest has been specifically developed for anomaly detection. Anomaly detection, it is an unsupervised machine learning algorithm, meaning that it does not use labeled data, which also fits a data set and is very good with high-dimensional data set, again, which is relevant for our data set. Thus, this identified more anomalies as compared to our other models. This project was done with the contribution of yours truly, Israt Munir, and my group members, Rabia Nadeem and Laiba Riaz. And this was done by the help of machine learning assistant professor, Dr. Jamil Ahmed, who is an assistant professor at the University of Management and Technology. So this was an explanation of how we implemented machine learning models for search query anomaly detection using machine learning models.